Thank you for coming. It's an honor for me to be here, where it all started for me, to present my recent work to all of you. So my name is Diogo Rodrigues. Today I'm going to talk about efficient methods for global solutions to optimal control problems. This is a work that I developed while I was at the Department of Chemical and Biomolecular Engineering, University of California at Berkeley. Currently, I'm working here at Técnico, Centro de Química Estrutural. So I'm going to give you a bit some details about my life as a student and researcher. So click here. So I started as a student in information systems and computer engineering between 2005 and 2008. I finished with a grade of 19, but then I moved to another degree, in this case in biological engineering, also here at Técnico. That was between 2008 and 2012. The first cycle was, I finished it with 18 and the second cycle with 19. Then I was a master student, trainee and temporary associate at Novartis in Basel, in Switzerland. That was between 2012 and 2013. I worked on different things still related to my previous background in biological engineering. So, for example, to optimize the activity of a human enzyme, or to optimize the production of antibodies through animal cell culture, and also to produce and purify research compounds produced by enzymes. Then later I moved to my current field, right, chemical engineering. I did my PhD at EPFL, also in Switzerland. That was between 2013 and 2018. At the end, I got a distinction for a remarkable thesis for being one of the top 8% on that year. While I was a PhD student, I worked on different subjects related to modeling, estimation, control, particularly for reaction systems. So some of the specific topics are here, for example, adaptive optimization, dynamic optimization. This is something that I'm going to continue talking about today. I was also responsible for co-supervising 4 students and teaching some courses such as control systems, process control, and system dynamics as doctoral assistant. Then after my PhD, I moved to KTH for a postdoc between 2018 and 2019, where I worked on modeling, control, and optimization of continuous bioreactors. Then I was a postdoc at the University of California, Berkeley, with the support of a fellowship from the Swiss National Science Foundation. That was between 2019 and 2021. That's the work that I'm going to present to you today, by the way. So that in that case, my work was related to control, dynamic optimization, and experimental design under uncertainty. And so more recently, I moved here to Centro de Química Estrutural at Técnico, where I have been since last year. And I'm working with Professor Carlo Pinheiro and Henrique Matos on modeling optimization and optimization of thermochemical energy storage in concentrated solar power plants. I would also like to mention some research projects for which I got funding in the past. So as I mentioned, one of them was the postdoc fellowship from the Swiss National Science Foundation for the stay at UC Berkeley. And more recently, I also received funding for the contract as junior researchers through what is called the individual SEC from FCT. and also a postdoctoral fellowship from Market Equity program from the European Commission. Also for a stay here at IST. We are still trying to decide how we are going to deal with these two, but these were approved projects. So just a few objective data about my publications. So I had 17 publications in scientific journals. So more specific details are given, 12 as first author, 1 book chapter as first author, 10 publications in conference proceedings, 9 of which as first author, 9 abstracts in conferences, and well, also the number of citations and H-index studies written. So my research interests are in the areas of process control, optimization, system identification, and optimal control. So this means it's in an interdisciplinary research in the fields of applied mathematics, chemical engineering, control engineering, and also related fields, even like electrical engineering. So now I'm going to the technical part of this talk. So this is the outline for today. So first I'm going to start with an introduction about the context. Then the presentation will be divided in 2 parts. I'm going to talk about optimal control in the first part. Then I'm going to move to what is called Bayesian optimal experiment design. Then I'm going to show some simulation examples related to both topics. I'm also going to show an application to a real system, plasma jets, and later I'm going to finish with some conclusions and future work. So regarding optimal control, the subject of this talk, what we can see is that many processes in the industry are batch processes, and their optimization leads to the so-called optimal control problems. And these problems are also present in several other related problems, such as estimation, control, and experimental design. So in these problems, what happens is that the decision variables represent some time-varying functions, such that a certain cost is minimized at the end of the time horizon, subject to some constraints, for example, during the trajectory of the system. One way to solve these problems is with the so-called direct methods, where we approximate the problem using discretization. The problem is that with these methods we can converge to local optima, which are significantly or maybe significantly worse than the global optima. So for this reason, some algorithms called global optimization algorithms are used. And here I give 2 examples. There are the branch and bound approaches that divide the space of decision variables until we converge to a global solution. And then we can also express the problem as an easier problem, such as a polynomial optimization problem, which can then be reformulated as a simple problem or a convex problem called the semi-definite program, or SDP. So the problem of these methods is that this complexity scales exponentially with the number of decision variables, and this is large in these OCPs. So for this reason, an approach has been proposed, which is the parsimonious input parametrization to reduce this number of decision variables. In this case, the idea is that we identify all the arcs, so parts of the inputs that can occur in the solution. Then we generate sets of arc sequences, and we describe each sequence with a small number of decision variables, which makes everything easier because it enables efficient computation of the global solution for each arc sequence. So the idea here is that we approximate the problem for each arc sequence as a polynomial optimization problem, or POP, and then this can be reformulated as a simple problem, an SDP. So this, in this talk, I'm going to show you how to do this for, in principle, complex dynamical systems. So the general formulation of the problem is as shown here. We are trying to minimize some over some inputs. We are trying to minimize a cost, which is given as a function of states x at given times, subject to some terminal constraints, also functions of states at given times, which are also subject to the dynamics of the system and also these constraints along the trajectory of the system. So what is known from the theory about these problems is that the solution is composed of arcs of several types. So for example, bang-bang arcs that are determined by input bounds or active state constraints, so which means that these conditions are just marginally satisfied, or free or singular arcs, which are determined by the system dynamics. So from this, we know that the number of plausible arc sequences is finite, and for each sequence, the idea is that we want to compute the globally optimal values of a few decision variables. So in particular, we want to compute the switching times between arcs, the final time, and the initial conditions of the free or singular arcs. So to choose the arc sequences, here in this talk, I'm going to assume, just to simplify, that we consider a single input, because this will affect the number of arc sequences. And what we call the plausible arc sequences here is are the sequences with a number of arcs no larger than a given bound and without consecutive arcs of the same type. So we denote the bang-bang arcs as shown here, depending on whether they are determined by lower or upper bounds. And we know that the number of plausible sequences is bounded by this number. And we can also assume that actually the bound on the number of arcs is somewhere between 3 and 5. So this is a reasonable assumption. And anyway, we can guarantee the global optimality among all the plausible arc sequences that we are considering. So now for the reformulation, we are going to express the inputs in each interval, each arc, by defining some augmented states, and then we combine all these states into a single vector, z, and this allows us to reformulate the problem not in terms of infinite dimensions, but in terms of some scalar variables, which I denote here as tau. And so we can see here that the cost and the constraints are become then some functions of these variables tau, and the problem does not depend on inputs anymore. Then the idea here is that we reformulate this original problem by expressing each one of these functions as a polynomial. And for this, we use interpolation to fit the values and the first order derivatives at the number of sample points. And what we can show is that this number of sample points is actually polynomial in the number of decision variables. And this is typically small because we have used this parsimonious parametrization. So then with these polynomial approximations, we reformulate the problem as this polynomial optimization problem. And since we know that these polynomial functions are approximations of the original functions, we can then also quantify the error induced in the optimal cost by this approximation. Then what we can also do is we take the solution to the POP and we compute the local optimum of the original OCP via optimization with the initial guess from the POP. And at the end, what can be shown is that the difference between the cost that we obtained and the globally optimal cost of the original problem is bounded as long as these approximation errors are bounded. So now I'm going to give you some clues of how this POP can be solved to global optimality. And the idea here is that we use the concept of sum of squares polynomials, which are simply polynomials that can be written as a sum of squares of polynomials. And the good thing about these polynomials is that checking their existence is equivalent to solving a complex or simple problem, simple optimization problem, an STP. So the mathematical result behind this reformulation is as follows. So let's suppose we have a set of polynomials and we define this set K as the set where these conditions are satisfied. And we also assume that one of these polynomials specifies a compact set. Then what we can show is that if this polynomial here is strictly positive for all tau in this set, then this function can be given as this combination of SOS polynomials. And this is a very useful result because it allows us to compute a lower bound, this psi, a lower bound for this function j that we want to minimize over all tau in this set K. Then what can be shown is that this can be formulated as an STP, which is a simple problem, and this can be solved efficiently for a small number of decision variables and degrees of the polynomials. Then we apply this theory to solve the POPs that come from the OCP, and we can obtain a certificate of global optimality and compute the global minimum and global minimum. Then we can also show that the size of the problem is polynomial in the number of decision variables, and this is equivalent to an efficient solution method. And as we have seen, then the solution to each POP allows us to compute the global solution of the OCP for a given arc sequence. And in turn, this means that once we know the optimal value for each arc sequence, we can check which sequence is the best one. And it can also be shown that since we are working with a small bound on the number of arcs, the problem for each sequence involves few decision variables, and this can be solved efficiently. So now I'm going to move to the second part about Bayesian optimal experiment design. So the idea in optimal experiment design is that we use a model to select experimental designs to maximize the information in our observations. And in particular, in the case of Bayesian methods, we use the concept of so-called expected utility. In fact, in this presentation, I'm going to use the expected utility based on the so-called callback-Leibler divergence from the prior to the posterior parameter distributions. And the challenge here is the numerical evaluation of this expected utility, which can be very expensive. And for this, what people have done is the construction of surrogates for the model outputs based on polynomial chaos. And now I'm going to show you a tractable approach for global solutions in the case of constrained systems. So the problem formulation is similar. We have a dynamical system described by this differential equation. We have the states x that depend on the number of uncertain parameters and the input vector u, which is bounded. And we collect some measurements of the system at some specific instance. And they are corrupted by additive measurement laws. So the idea is that we use a Bayesian perspective to design the variables that comprise the inputs and some parameters that affect the initial conditions. And for this, we use the so-called Bayes rule that specifies the change between a prior PDF, or probability density function, and a posterior PDF, depending on the likelihood function. So the optimal design is based on two parts. One is the maximization of that expected utility that I mentioned, and the other is that some chance path constraints need to be satisfied. This means that these constraints along the way are satisfied with a certain probability. To choose the expected utility, we want to maximize the mutual information between parameters and outputs, or the expected gain in Shannon information. And for this reason, we use this utility function that is defined as the KL divergence, as I mentioned. The problem is that this is intractable from a computational point of view, and the goal is to approximate it as something that can be solved to global optimality. So, as I mentioned, this is the problem arises from this integration in both spaces, the observation space and parameters space. And for this reason, I'm going to work with some relatively mild assumptions about the prior PDF and the observation noise. So the first assumption is that the noise realizations are given as shown here. They can depend on multiplicative noise, and they are drawn from a distribution with this PDF pi, which means that the likelihood function then also depends on pi. And then the second assumption is that the prior distribution of the parameters is just some multivariate distribution. So using these assumptions, the optimal design can be approximated as the design shown here, with a utility function that simply depends on the PDF pi that I mentioned before. What can also be shown is that this utility function is simply given by multivariate integrals over the parameter space, and the only approximation involved here is the Monte Carlo integration in the observation space. For the chance constraints, we can perform an approximation using these moments of the path constraint functions. And then the problem is that, as we have seen, we want to maximize the expected utility subject to moment constraints, but both depend on integrals over the space of parameters. And so for this integration, we can use an efficient approach based on sparse stochastic collocation, which is the multivariate version of Gaussian quadrature. And for this, we express this integrated function in terms of orthogonal polynomials. And this allows obtaining a method that uses fewer points than the usual method of polynomial case extensions. Then all the approximate functions can be written as functions of the states for the given realizations of the parameters, and we denote all these states as S. And finally, what can be shown is that this Bayesian OED problem can be approximated as an OCP, as shown here. And this allows using all the methods that I have shown in the first part of the talk. So now going to simulation examples. First, I'm going to show an example of optimal control of a batch reaction system, or in fact, semi-batch reaction system. So with 3 reactions, and the goal here is to maximize the final amount of the product C, subject to constraints on the final concentrations of this reactant B and the byproduct B. The input is the volumetric inlet flow rate of B, subject to bounds, and we formulate the problem mathematically using the so-called extents as states. So here in this figure, I show the optimal input trajectory for this optimal control problem. With the solid line, it's an approximation using a linear function of time, and the dashed line uses the analytical expression for the input in this arc. So the solution is composed of 3 arcs. In the first arc, the input is given by the upper bound. In the second arc, it is a singular arc, and in the third arc, it is determined by the lower bound. It can be shown that this the local optimality of this solution is given by the optimality conditions for these problems, the Pontryagins maximum principle. And then now we apply the proposed approach for the 6 plausible arc sequences with a number of arcs no larger than 3. This is actually what is shown in this table. We have the 6 arc sequences, and for each one of them we have the execution time, optimal cost, and optimal values of the decision variables. So this execution time includes the evaluation of the sample points needed for the polynomial approximation. And for each sequence, we can extract the solution to the POP and then certify its global optimality and obtain the solution to the OCP. And we can see here that this is actually the best arc sequence, which actually corresponds to the one in the previous slide. And this way we can show that this is the global solution with no more than 3 arcs, which only requires solving 6 problems in parallel and in less than 40 seconds. Now, the second simulation example is related to Bayesian OED. This is related to a Lotka-Volterra system, so a prey-predator system described by nonlinear differential equations, where the states describe the prey and predator populations with some uncertain parameters that follow a beta prior PDF. We also know that we measure the second state at the end of the time horizon with a certain error, which is partially multiplicative. We have an approximate constraint for the first state along the trajectory. The input is allowed to be in a certain interval, and again we investigate all the arc sequences with a number of arcs up to 3. So here we have a contour plot of the prior PDF, and the crosses show the integration points that are used for the integration in the parameter space using Gaussian quadrature. And this way we can achieve exact integration of polynomials up to degree 9. Then here in this figure we see the optimal input trajectory in blue, the state trajectories for the different parameter realizations in red, and we have the trajectory of the state subject to a constraint in green. This solution is again composed of 3 arcs. The first one is singular, the second one is determined by the upper bound, and the third one is determined by the lower bound. And we can see that this measured state is sensitive to variations of the parameters, which is good. And we can also see that this upper bound for the first state is marginally satisfied as required. So again, the same table for this example. Again, the execution time includes the evaluation of all the sample points needed for the polynomial approximation. We can again do the same for each arc sequence, extract the solution to the POP and then the solution to the OCP. And for the optimal designs, we can see that our approximation of the expected utility is always underestimating the real one, which is good. And we can see that the optimal arc sequence is the one that I showed in the previous slide. This way we can show that this is the global solution with no more than 3 arcs. And in this case, we only need to solve 6 problems in parallel in less than 1 hour, which is reasonable for experimental design. So now I'm going to show you an example of application to a real system. So this is a plasma jet that is in a lab at UC Berkeley. This plasma jet consists of this tube surrounded by this copper electrode. Helium flows through the tube, and then we apply some AC voltage to the electrode to achieve ignition. The plasma is directed onto a metal plate under the tip of the tube, and then we manipulate the surface temperature by manipulating the applied power. And for this, we use the microcontroller that manipulates the real physical value, which is the applied voltage. So in this figure, I show examples of real-time control experiments with the system. And in this case, we can see that it's in an iterative approach to achieve a certain thermal dose with this system. So in this figure, we can see the evolution of the temperature for each iteration. This is the thermal dose, and this is the input. So there are certain constraints that need to be satisfied for this problem. And we can observe two things. First, here regarding the temperature, we have this bound, and the control strategy that we apply in real time is able to track this upper bound despite the noise and the lack of knowledge about the true system. And after a number of iterations, in fact 5, we can see that the approach converges to the desired dose, despite the fact that we are using a simple physics-based model in the description of the OCP. So now some conclusions about what we have seen. I have presented an efficient global solution method for OCPs, which relies on the enumeration of plausible arc sequences. We have seen that this is based on the approximation of costs and constraints for each arc sequence using polynomial functions. This allows reformulating the problem as a POP, which contributes to an efficient implementation, since this can then be reformulated as a hierarchy of convex STPs using this concept of SOS polynomials. And this allows dealing with problems with a potentially large number of states. Regarding Bayesian OED, we have also seen a method for globally optimal solutions, in fact for arbitrary prior and observation-wise distributions. In this case, we use the approximation with Monte Carlo integration in the observation space to deal with the problem related to KL divergence. And this allows dealing with designed initial conditions and also chance path constraints, which are challenging problems. For the integration in the parameter space, we use a sparse stochastic collocation scheme, which approximates this OED problem as an OCP. And these methods have been demonstrated on both simulation examples and also a real experiment. So now I would like to take just a few slides to mention my future work, also related to this subject. So, so far I have only talked about models, but we know that due to the so-called model mismatch, the model cannot represent the true system. So this means that, in fact, when we implement the solution from the model, this can lead to suboptimal or even infeasible operation. And so the interesting research question here is, how can we guarantee at the same time global optimality, but also robustness with respect to model mismatch? And how efficiently can this be done? And this is, in fact, a challenging state of the art problem with both theoretical and practical importance. Well, across many tasks in process engineering and for the industry as a whole. To achieve these goals, or to answer these questions, we can pursue the following research goals. So first of all, develop the methods to compute global solutions, then also achieve robustness with respect to the problem of model mismatch, and then also very important, application of these methods and tools to process industries. So regarding the first part related to global optimality, as we have seen, we can deal with the high dimensionality of the original problem using a parsimonious parametrization. So the novelty of this part of the project will be the fact that we are trying to deal with the multiple input case, which is more complex, and also the fact that we are going to achieve at the same time global optimality and deal with the presence of model mismatch. For this, we need to exploit the small number of decision variables. Because, for example, this allows using efficient methods for function approximation. So some examples, we have sparse polynomial chaos, artificial neural networks, Gaussian processes, and there are others. Then, of course, this is allowed by a small number of decision variables, and the idea is to extend this not only to the case of multiple inputs, but also stochastic disturbances. Then, in another part of the work, it would be important to ensure convergence to the optimum of the true system, the one that we want to optimize. And this can be achieved by using adaptive optimization. So there are a number of methods related to adaptive optimization. So usually what people would do is simply to estimate the model and the parameters again, but this may fail to converge to the true optimum. And then there are also other approaches related to directly adapting the input, but this is difficult to apply in this context where the decision variables specify some, for example, some switching instance. So in this case, I propose the approach based on modifier adaptation, which is an adaptive method that requires the experimental costs and constraints and also their gradients with respect to decision variables. Of course, this benefits, again, from a small number of decision variables. And the idea is that after each modifier update, the modified model can be used again for optimal control. And another interesting question is if we can use Gaussian processes to describe this model mismatch. Now, finally, regarding the validation, it would be important to validate all these methods and tools in real industrial processes. And the current idea is that this could be done in the chemical or pharmaceutical industry. And the idea of this work is that we want to present this feature of global optimality in the presence of model mismatch as something that can be realistically achieved in the context of complex problems. So the idea is to develop efficient and user-friendly tools and to publish general methods and their applications. So of course, this is not enough. Then we also want to validate this on real problems. And so as a possible impact of this work, we predict that this will have a relevant impact on the efficiency of the industry and also on process engineering and optimization as a whole. So here we have some references of this work. So finally, I would like to thank Professor Ali Mesbah from UC Berkeley and also his research group for all their support and collaboration throughout this work. I would also like to mention the financial support from the Swiss National Science Foundation for this work. And last but not least, I thank you all for attending this talk and for your attention, and I look forward to your questions. Thank you.